737 and it doesn't exist in your e-textbook. So you want to change, just make a quick change there to section 3.4. Okay, so I want to talk briefly about homework problem number 12. In the last night's homework, and it asked you, and everybody probably got a different parabola to graph, but they all look something like this: 5 minus x squared, 4 minus x squared, 7 minus x squared, right? They all had a form like that. So if we work, say, with this first one, and you just quickly, you know it's a parabola that opens downward because the leading coefficient is x, is negative. The y-intercept when x is 0, this is 5. And it says that your job is to find the maximum area now of a rectangle that's inscribed under that parabola with its base along the x-axis. All right, so here's some point x1, and what would be the y value for that x1? 5 minus x 1 square, right? You just plug it into your function. F of x is 5 minus x squared. And then over here, you have another value, x2, and you're at 5 minus x2 squared. So those would be your coordinates for these upper corners, which it was asking you to find. Okay, so to find the area of a rectangle, what do you need? The height, in this case, the height times the width, or the length times the width, right? We're calling it height here. Your book calls it height because they're looking at this value right here. Okay, so what is this height right here? What is that height on both of these? What value is this right here? Which of these two values is it? 5 minus x squared, right? And since these x's are just opposite of each other here, you're still going to get the same value there, 5 minus x squared. That's your height. That's your length, your height, whatever you want to call it. Your width here, well, what's the width? Here's 0, and you're going out to x, so what's that distance? X. You're going out the same distance here, x, so what's your base? 2x. So your area in terms of x is 2x times your height. Now, in terms of maximizing, you're only used to maximizing areas that are quadratic, like the problem you had the class before. But when you multiply this out, you get 10x minus 10x cubed, right? Oh, 2x cubed, sorry. So you don't know how. I mean, you can't, I mean, if this was a square, if it was a quadratic, you just find your vertex. Voila, you find your maximum area, but this is a cubic. So you can't do this algebraically. Now, next semester, when you're in calculus, you'll do something called take the derivative of this, set it equal to 0, and it's as easy peasy. Okay, it really is much easy, very easy with calculus. So the only thing you can do now is remember, you can use your technology to find answers. So if you go to GeoGebra or Desmos, or if you happen to have a graphing calculator, put in the, this is from my other class, put in the area which we just found, which is a cubic. So you should start to, we're working with polynomials now, so you should start to have an idea of what that cubic might look like possibly. So what did we just find? Was it 10x? 10x minus 2x cubed. Okay, so there's your cubic. You have two turning points. I haven't put that in yet. Okay, your leading coefficient's negative, so your right arm's down, your left arm's up, everything we talked about the other day. And to find the maximum area, your maximum area is right here, because this is a graph of the area for various values of x. Now, it doesn't make any sense to have any values of x that are less than 0, right? Oops, how'd I do that? Oh, that's interesting. Wow. How did I do that? That is like so cool. Wow. All right. I must have hit a circle or something up there. So we're really interested in this part of the graph, and we're not even interested in negative values. We're interested right there. That's the area we're interested in. And we're interested in finding that value. Well, that's called an extrema. So you just go extrema. And if I didn't type so fast, you'll see it gives you the command right here, polynomial. My polynomial is called capital A of x. You put that in. And hopefully you type better than I do. Still got the 9 there, don't I? Okay, let's try this again. X. Good. And it will give you two values, a negative value and then a positive value for x, and it's 8.61. Okay, that would be the maximum area. All right, now if you know calculus, you're going to get the exact values. You'll get something like square root of 5 over 3 times 2 for one of your dimensions, and what was the other one? 10, I can't remember. I did it last night. So you can get the exact, this is again just an estimate. All right. But that's the only way you can do this right now. So this will give you, remember this problem when you go into calculus next year and you do something called optimization, which will be spread through the whole course. You're always trying to optimize maximum areas, maximum whatever you're talking about. Okay, and you can do this type of problem. Ask either Caitlin or Ian, and you should be able to do this pretty quick in 107. I mean 201.
So it'd be safe to say we won't see that.
Not unless I give you a graph or some kind of graphing utility to use, which I won't. But I might give you a graph and ask you to find the maximum area, or if it, you know, I mean, I could play this lots of ways. But I don't know. I haven't made up the next quiz or the next test yet. Like I said, I'm a couple classes ahead of you at this point. So that's we've got class notes until Friday. Woohoo! I got a great weekend ahead of me. So, okay. So again, I wrote GSP here. What was I going to do with that? I don't know. This is, again, the last thing. This topic is the last topic we have that's a review of 107, and it's rational functions. And if you recall, we spent a couple of days, and you had quite a few lesson activities in 107 if you recently took 107 with us. Some of you haven't. And I asked you to make this vertical line through x equals 1 as a dotted line, meaning that the graph does not ever cross that line, this particular vertical line. It gets really close to it. And I asked you for what values of x, hopefully you saw the plural there, some of you missed it, for what values of x is this function undefined? So this function is not defined at x equals 2 because you see a hole in the graph. And so it's not defined for x equals 2. And it's also not defined when x is 1 because of that dotted vertical line. And we're going to spend a lot more time today talking about each of these. Okay, so this is the two places where the function is not defined. Write an equation for the vertical asymptote. That's that vertical dotted line. The equation is x equals 1. And then the horizontal asymptote is the line that your function approaches in the long run, way out here when x is large in the positive direction and then the negative direction. And you see that in both of these directions, that graph is getting really close to 0, y equals 0. So that's your horizontal asymptote. Okay. And again, if this is not familiar to you, you can, we will go over all these ideas. So let's start with an application problem. Shane, just in time. Number 1.
We started section 9 about the rational functions. Here's an example.
Luddite. Do you know what a Luddite is? Oh, look it up. It's interesting.
Okay.
So in today's world, it would be anybody who kind of like refuses to embrace technology at this point. You would be called a Luddite.
So Luddite sums up for itself and cost of $30 per month plus 10 cents per minute. Suppose one day talks for X minutes for a month. Find a function that represents their total cost per month.
This should I feel more comfortable saying average cost per minute. All right, so total cost for the month. Let's assign a function, C of X, and what would that total cost per month look like? Anybody, if X is the number of minutes? 30 plus 10X. 0.10X or 0.1X, and the 10 would be if we were getting our bill in terms of cents, right? Pennies, but we usually get them in terms of dollars, so 10 cents is a tenth of a dollar. Okay. Now the average cost per minute, how would we figure that out? So this is our total cost. How would we figure out the average? Divide it all by the number of minutes you talk, right? And typically economists will, when they're talking about average costs and stuff, they put the little, like when we put the little bar in statistics over X or whatever, that stands for the average. So yeah, it's 30 plus 0.10X all divided by the number of minutes. So geez, if you talk for 1 minute, you're going to be paying $30.10 for that 1 minute, right? If you talk for 100 minutes, you're going to be 40 over 100 or 40 cents per minute. So the more you talk, what happens to your average per minute? The more you talk, the average cost per minute. I saw a thumb like this. Is it going up, the average cost? If you don't talk at all, you're paying $30, right? If you talk for 1 single minute, you're getting 30 plus 10 cents. $30.10 over 1 minute is $30.10, right? The more you talk, yeah, we can't even talk about zero here because of the denominator, right? But for 1 minute, it's $30.10. What is about 2 minutes? Well, 2 minutes is what? $30.20 divided by 2. So it's already going down, right? So this is the kind of thing, if you had a graphing calculator, let's take a look at how you could look at this with a graphing calculator. We can also look at this with any of your free software packages. So let's just get a sense here. 30 plus 0.1x. And I want to put this all in parentheses because I'm going to be, oops, not that way. Let me start again. Parentheses. 30 plus 0.1x. The whole thing divided by x to get the average cost per minute. All right, so let's see here. I want to start my table not at 0, but at 1, because I can't divide by 0. And we'll have an increment by, want to do 10 minutes, say, instead of a minute at a time? The way people talk today, I should probably have 100 here. Okay, and let's take a look at our table. So after 1 minute, we already talked about that. But look at after 11 minutes, we're down to 2.8 cents per minute. After 21 minutes, 1.5, right? And you can see as we go along here, what's happening to the value of my average cost per minute. What's it approaching? 0. Yeah, the more you talk, the less that $30 has the impact, right? That $30 is being spread out over 431 minutes. So it's getting smaller and smaller and smaller. Okay? The impact of that $30 as you talk more and more and more. Okay, so we can see, will we ever be 0? No. Ooh, someone's thinking ahead. It won't ever be 0.1 either. Well, that's an interesting thing to talk about. Yeah, so let's talk about all that. Okay, so, this was supposed to be in your group, so I did the first question for you. In your groups, use the formula from above to try to figure out what happens to the average cost per minute, as the number of minutes gets large. So how could we write that? I want to start using limit notation because it was a weakness I saw on the test. So we're looking at the limit as the number of minutes gets bigger and bigger and bigger. So that's how we write it. the limit as x goes towards infinity of, what's our function called? C bar of x. Is this approaching a value? And that's what you put there. Then I want you to think about, and hopefully someone at your table has a graphing calculator. If not, I can get one out of the back cabinet. Then we want to think about the limit, if it exists, as x goes towards 0. And let's look at it coming in from the right-hand side of 0, because we can't talk negative minutes. And that's what that little plus means right there. C bar of x. So get out some calculators on your table. Spend a few minutes discussing this, and then we'll come back and look at it.
So the 0 with the negative means you're approaching from 0
from the left, yes. Sure. And Hazel, I'm sorry, I forgot to record all of it. Hope you're feeling better. Yeah, from the left, yeah. Oh no, it's negative, and I screwed up. That's negative infinity and positive. Thank you. No. It's going down, it's decreasing. I probably said it, but wrote it wrong. Yeah. Okay, so this is what you have to keep in mind, because it makes graphing rational functions so much easier. You don't have to deal with all of those sign tests anymore, like, am I positive to the left, negative to the right, what's happening? You can just look at the degree of the multiplicities in the denominator, and if it's odd, on one side you're decreasing and on one side you're increasing, or vice versa. So it's a really quick way to get a sketch of some of these rational functions. All right, let's write the cost per minute function. I already did this. This is what I did before as two other functions. So I did it this way earlier. So we could look at the behavior as x got really large and as x went towards 0. So basically now we're ready to define a rational function. So notice, if you look at it in this form, it doesn't look like the ratio of two polynomials because it's two separate terms. But we know that should have an x here. This can be combined into this one function, into this one fraction. So this is what we call a rational fact. Back up. This is what we call a rational function. Notice you have the word ratio in rational, and a rational function is the ratio of two polynomial functions. So notice here, this top function is a linear polynomial function, right? And the bottom's linear. These are both linear. And the fact that they're both linear, it's this part of your linear, your rational function, where that shows you your horizontal asymptote. Because when the degree in the top and the degree in the bottom are the same, as x gets really large, your function approaches 0.10 divided by 1, because this cancels to 1. You always look at the leading coefficients. All right, so let's take a look at each of these rational functions. All right. Oh, we're going to try to determine which ones are rational. Is the first one rational? Is it the ratio of two polynomial functions? You got what? You got a what? A quartic on top and a what on bottom? Quadratic, right. So, yep, this is definitely yes. What about the next one? How can I rewrite this expression? So I'm looking at division. Jenna? 3 over x to the 4th. So I have a polynomial on bottom, which is a quartic. And what's the degree on top? 0. Because if it was 1, what would I see here? X, right, because x has a 1 on it. So I see 0 x's. I see no x's, degree 0 on top. Degree 0 on top, it's a constant, degree 4 on bottom. Okay, so that's definitely rational function. Sometimes we got to do a little work to massage the expression to see if we can make it into one polynomial divided by another. So don't be afraid to smush it together or to do a little algebra work on it. What about the next one? Write y or n on your paper. I won't look. Maybe I'll get 2 different answers here and we can have a great discussion. I don't know. Yay or nay? What do you think? No. Anybody say yeah? Nobody says yes? Can I do that? Can I? Is it the same function? Is that a cubic on top and a 0-degree polynomial on bottom? I mean, we would call this a cubic polynomial. You know, we wouldn't, because when we think of rational functions, we really think in this way, like this, or some other way. But technically, that is a rational function. But it wouldn't be one I'd expect you to say yes to. All right, how about D? I see a ratio. I see a linear function on the top. Why not? Hannah? Yeah, so what kind of function is this? Exponential, right. So it's not the ratio of 2 polynomial functions. The top's a polynomial, but not the bottom. Nope, doesn't work. What about the next one? Does it have the form of a polynomial divided by another polynomial, a single fraction right now? That's not a hard question. Do you see a big plus sign there? Yeah, so it's 2 separate fractions, right? It's not a single fraction. Can you smush them together? You can make them into the common denominator of x times x plus 3. So on top you'd have x plus 3 multiplied this first fraction by x plus 3 over x plus 3, and then this fraction by x over x. So we'd get x plus 3 plus x, which is 2x over plus 3. So yep, now it looks like a rational function, so the answer is yay. All right. This next function in its current appearance is not rational, but how can we make it be rational? Well, we can simplify it. Anytime we divide by anything, it's the same as multiplying by the reciprocal of that denominator. So this is 2x plus 5 over x plus 1. So that's also a rational function. All right, so let's move along here. I've been taking too much time on this other fun stuff. Horizontal asymptotes are the little places that always kind of get us a little bit, but your thinking now is expanding and thinking more about end behavior. That's all we're talking about here. Does our function have a limiting value as x goes really large in the positive direction and large in the negative direction? Okay, and there's a theorem. It says if the degree of your numerator is bigger than the degree of your denominator, the top, remember, we're always with the polynomials. Our end behavior is determined by the leading power function, right? So if we have this first problem here, oops, if we have this one right here, x to the 4th, if we turn this into a function notation, and we ask, does this have a horizontal asymptote? When x is a billion or a negative a billion, we don't care about that -1 and the +1. And this would simplify to what if we use our exponent properties? X squared. So as x gets large in the positive direction and large in the negative direction, what is this function approaching? Infinity. It doesn't have a number that it approaches. Okay, so anytime your numerator, the degree of your numerator is bigger than the degree of your denominator, you do not have a horizontal asymptote. No horizontal asymptote. Let's look at this next one. So what can we say about the degree of the numerator and the degree of the denominator? The degree of the numerator was what again? 0. And that 0 is less than 4. So the degree of the numerator is much smaller than the degree of the denominator. So as x gets really, really big, what's going to happen to the value of that fraction right there? It's going to get wicked small and fast. You put 1,000 in there and raise it to the 4th power, 3 divided by that number, I can't even like show you the distance between my thumb and my forefinger, right? So here, anytime the degree of your numerator is bigger than the degree of your denominator, your horizontal asymptote is always your x-axis, which is the equation y equals 0. Now let's take a look at this final one right here. 2x plus 5 over x plus 1. And let's call that g of x. Here, the degree of my numerator is equal to the degree of my denominator. They're both linear polynomials, right? So again, when x is really, really large, I give you $1 billion. You don't care if you have $1 billion plus 5. These numbers right here have no effect on the overall value of this ratio. So you can totally ignore those. And now you say, what happens to this function as x gets really large in either direction? We'll just look at one for a minute. What happens to g of x? Well, if you put in 2 times 1 billion over 1 times 1 billion, you get 2. It's the ratio, it's always the ratio of your leading coefficients. Because remember, you're looking at just these 2 power terms, 2x over 1x, and that reduces to 2 over 1. So the way they say it sounds confusing, but when you think about it, it isn't confusing. Just simplify it, it's 2 to 1. The horizontal asymptote is the leading coefficient of your numerator, of your leading term, 2, divided by the leading coefficient of your denominator, 1. Now, vertical asymptotes, when do they show up? Vertical asymptotes may show up when you find a value of x that makes your denominator 0. Okay, that's when they may show up, but not always. So let's take a quick look back here at some of these examples again. I'm going to erase some of this stuff. So can this first denominator ever, is there a real number that will make that first denominator 0? What value? Negative 1 square is 1. 1 plus 1 is? Real number. Or no real numbers. X squared plus 1 will never be 0 in the real number system. So this has no vertical asymptotes. What about B? What's my vertical asymptote there? 0. What's 0? A vertical asymptote is a line, a vertical line. So I need an equation. X equals 0. That's my vertical asymptote. My y-axis. Is C ever going to have a vertical asymptote? It's a cubic. It's a polynomial. Any bumps or holes or jumps or vertical asymptotes with a regular old polynomial? Nope. It's being divided by 1. So no problem there. D is not even a rational function. Okay, this one we smushed together. What was it? 2x plus what? Do you remember? 8, 3 over x times x plus 3. So here you got 2 spots that can make the denominator 0, 0 and negative 3. So you have 2 vertical asymptotes. Okay, at x equals 0 and x equals negative 3. And this last one, we had 2x plus 5 over x plus 1. There's 1 vertical asymptote, and that's at x equals negative 1. All right. Now, the only other thing you have to think about are your vertical and horizontal intercepts. Your vertical intercept is always the same way you find it. You plug 0 in for x, and assuming x is part of your domain, you get a number. And that's your vertical asymptote. Now, here's the big one that students often forget. If you have 0 divided by a number, you get 0. So if 0 is your output, then to find your horizontal intercepts, your x-intercepts, you want your output to be 0. You just set your numerator equal to 0 to find your horizontal intercepts. Set your numerator equal to 0. That's your x-intercepts. So if we were looking at this one right here, 2x plus 5, the only way I can have a horizontal asymptote here is when this equals 0. And so the only thing I have to pay attention to is when does my numerator equal 0? And when my numerator equals 0, my function is 0. So 2x plus 5 equals 0 when x is negative 2.5 or 5/2. So that would be my x-intercept, negative 5/2. So let's graph one of these things. Put it all together. All right. Whoa, really? Oh, I already talked about that. Where are we going to graph something? Oh, is this in the demo or is this in lesson activities? It is. All right. All right. So let's take a look at this function for 1 second. If I asked you what the domain was for this function, what would you say? What's the domain? Set of all real numbers, but x can't be a 2. And let's look at what happens when we put 2 into this function. Let's see what happens. We get 4 times 0 on top and 0 on bottom, which is 0 over 0. Anytime you put a value into your rational function and you get 0 over 0, this is a special situation. Because what it says is that 2, if 2 is a 0 of the function, it's a factor of the function. Remember that from 107? So if you have a 0 in the bottom, you have a factor, x minus 2 in the bottom, and you have a factor in the top. So you have a common factor top and bottom. Whenever that occurs, you have what's called a hole in your rational function. There's a hole at 2 because this can simplify to be x squared. So if you were to graph this function, it looks just like your baby parabola x squared, except when you get to x equals 2 and you go up to make it 2, 4, you put a hole at 2, 4, and then you continue on. Because 2 is not part of the domain. So this does not have a vertical asymptote. It has a hole. And you'll have a fancy name for that when you get to calculus. It's called a removable discontinuity. Woohoo! All right, yeah, woohoo. All right, so values that make your denominator 0 don't always produce a vertical asymptote. Sometimes if that same value makes your numerator 0, you're going to get a hole there at 2, 4 in this case. And we just talked about significance of zeros in the numerator. That's what gives us our horizontal asymptotes, is when our numerator is 0. Excuse me, our homicidal, yes. Homicidal intercepts, horizontal intercepts. When you set your numerator equal to 0, that's the only time you can get your x-intercepts, your horizontal intercepts. All right, let's take a look at this graph below here. When you see something like this, you don't freak out, okay? You notice it's already factored for you. That's good, because the factorization first helps you to see, are there any common factors top and bottom to tell you if you have a hole? Any common factors top and bottom here? Anything, same factor in the top as bottom? No. So we're not going to have any holes, and if you look at this graph, you don't have any holes. What values are excluded from the domain? Those are the values that make your denominator 0. Well, When does x plus 3 equal 0? And when does x minus 2 equal 0? Well, this one equals 0 at negative 3. So that tells you at negative 3, you're going to have this vertical line called x equals negative 3. That's your vertical asymptote. That's one of your vertical asymptotes. Okay. Your other vertical asymptote is located at x equals 2. How do you find your x-intercepts? Set your numerator equal to 0. So the horizontal intercepts, or what you commonly know as your x-intercepts, just set your numerator, x plus 1 squared times x minus 3 equal to 0. Take each factor and set it equal to 0. So at x equals 3, you've got a x-intercept, and at x equals negative 1, you have an x-intercept. Now this graph is already done for you, but what the heck, how would you even try to graph this? Well, we've left out one other important idea here. We've left out horizontal asymptote. So look at the degree of your numerator. The degree of your numerator is what? Is it 2? Do you just see a square there? 3, you see it, something square and something to the what power? 1. So the degree of my numerator is? The degree of my numerator is 3. All right. Woohoo! Degree of numerator is 3. What's the degree of my denominator? 3. Woohoo! They are equal, so it's the leading coefficients, and aren't we lucky, because the leading coefficient is just 1 on the top and 1 in the bottom. Even if I multiplied all that junk out, I would just have an x cubed there to lead off, and I'd have an x cubed to lead off the bottom. So 1, this horizontal asymptote, is what this blue line approaches as I go way out here, as x gets large in the positive direction and as x gets large in the negative direction. Okay, so it's way out in the end, so you don't have to bother putting those dotted lines through. Now, this is where the good stuff happens. So you're out here, you know, you could be somewhere out here a little bit below your horizontal asymptote and cross it. It's totally possible to cross your horizontal asymptote. And I could check for that, but I don't want to take the time right now. So you're way out here, you know your horizontal asymptote, and you're moving in towards your vertical asymptote, which you know you're going to go crazy at. But here's the good stuff that I told you earlier, and I wrote it out for you up here. Here's your 1 over x function. Here's your reciprocal function squared. So look at the degree of this factor right here, the multiplicity. It's 2, right? So that means you're not going to change sign. So you know as you come in close to negative 3, you're going to increase without bound. When you take a little baby step to the right, you're not going to come down here because you're even. You're still up here. And then you head down towards your negative 1. And then what do you do at negative 1? You look up in your numerator. At negative 1, you're quadratic. So you bounce right back up, go through your y-intercept, which you can find easy enough, and then you head up towards your vertical asymptote. Now, look at x minus 2 on the denominator. Odd or even? Power. Odd. It's going to act just like 1 over x. It's going to act like this. It's going to change sign when you take a little step to the right. So you don't even have to do all that business anymore. Am I positive or negative to the left or right? You step down here, and then what do? You know you got to eventually head up here, but you got to go through your x-axis at 3, 0, and then you head out. Remember, we're just doing sketches. We're not getting these things exact. All right, so that's everything you ever need to know about asymptotes. And you know what? We didn't get to talk about slant asymptotes last semester. I'll leave it there for you if you want to look at it. This is kind of an interesting thing. When your degree in the top is one more than the degree in the bottom, you'll get a straight line as an asymptote. Your book also has it. It's optional. So I've written everything out for you here, the summary of graphing rational functions will be right here for you whenever you need it. And since we're almost running out of time, why don't you just try to get number 1 done. See if you can sketch this particular rational function while I'm here to help you.